Welcome to an introduction to thermodynamics, the branch of physics that deals with heat, work, and temperature. Thermodynamics studies how energy transfers and transforms within systems. At its core, thermodynamics examines how energy flows between systems and their surroundings. A fundamental principle in thermodynamics is that energy cannot be created or destroyed, only converted from one form to another. This is known as the first law of thermodynamics. Thermodynamics governs countless processes in our world, from engines and refrigerators to weather patterns and even living organisms. Let's look at a simple example of thermodynamics in action: a pot of boiling water. Heat energy from the stove transfers to the water molecules, increasing their kinetic energy and causing them to move faster. This transfer of energy from the flame to the water demonstrates the core principle of thermodynamics: energy transforming from one form to another. The four laws of thermodynamics form the foundation of how energy and heat interact in our universe. The zeroth law states that if two systems are each in thermal equilibrium with a third system, they must be in thermal equilibrium with each other. This means that if System A and System B are both in thermal equilibrium with System C, then System A and System B are in thermal equilibrium with each other. This fundamental law establishes the concept of temperature and allows us to use thermometers to measure and compare thermal states. The first law of thermodynamics tells us that energy cannot be created or destroyed, only transformed from one form to another. This means energy is conserved in all processes. It can change forms, like thermal, kinetic, or potential energy, but the total amount remains constant. For example, when an object falls, its potential energy transforms into kinetic energy, but the total energy remains the same. The second law of thermodynamics states that the entropy of an isolated system always increases over time. In practical terms, this means heat naturally flows from hot objects to cold objects, never the reverse. Eventually, both objects reach thermal equilibrium, with entropy at its maximum. The refrigerator is a practical application of the second law. It uses work input to move heat from a cold space to a warmer environment. The first and second laws together explain why perpetual motion machines are impossible. They would need to either create energy or reverse the natural flow of entropy. The third law of thermodynamics states that as a system approaches absolute zero temperature, its entropy approaches a constant minimum value. As temperature decreases toward absolute zero, molecular motion almost stops, and the system becomes more ordered. At absolute zero, a perfect crystal would have minimum entropy, but the third law tells us we can approach absolute zero but never reach it.